So it's my pleasure to again introduce Nicolas Bergeron to give his fourth lecture on the Sczech cocycle and hyperplane arrangements.
Okay, so thanks. So today I will speak on the Tits and Satake compactifications and relation with modular symbols. And of course, in relation with what I have already discussed so far. So let me remind you quickly what we have done yesterday. So yesterday we produced a form which I called eta, which is a 2n-1 form, which is closed. So maybe stick like that. A closed form on X, which is a symmetric space associated to SL and C, cross Cn minus 0. And most importantly, this form is G invariant, where G is GL and C. And now I'm claiming that this form that we constructed yesterday, in fact, represents an equivariant cohomology class. An equivariant cohomology class. So it's our preferred lift, if you want, that we discussed in the first lecture. So that at that time I denoted it as affine for Sczech, and because we are in the affine situation. So it's 2n-1 equivariant cohomology class of Cn minus 0. So maybe I should explain a little why this is so, because here I'm going from a continuous cohomology somehow to discrete cohomology. So how do you get from eta an equivariant form like that? And the idea is to construct a map from the space that we have considered, e.g. cross C minus 0. And in fact, I will consider the geometric realization of this simplicial set. So you really put simplices each time you see an abstract simplex G0 up to GK, and you glue using the gluing map that I described last time. And we will map this space into X cross Cn minus 0. And the way we map this, each time we see a simplex associated to G0 up to GK and an element Z in Cn minus 0, then we map it to a geodesic simplex, which I will denote delta G0 up to GK, Z. And this geodesic simplex is associated to a choice of a base point, to some base point in X. So so the map, as you see, is something like that. You choose a base point in your symmetric space, and you move it by the element, in fact, G0 to preserve the action. Remember that G acts on the right on the simplicial set. So I take a base point that I will denote, let's say, T0, and I move these, and I take a geodesic simplex etc. in the symmetric space, and it preserves the gluing map on the left hand side, and now I have a closed form on x cross c n minus 0, so I can integrate on these simplices, and that's how I build my cocycle. So in other words, that's how I build that the cocycle, which is now a simplicial differential form. I can pull back the so let me call it rho, and I can pull back, and this gives a simplicial differential form. That represents a class that it's closed because eta was closed, and that represents a class in the equivariant cohomology group, and that's the affine class. But there is some issue with this class. I mean, it's a very nice class. It doesn't depend. It's not hard to show that it does not depend on the base point, because if you change the base point, then you are just doing some homotopy inside the symmetric space. You can move everything from one base point to the other in a G equivariant way. Because it's important here that eta is G equivariant. That's why it defined really a simplicial form on the quotient. So on EG, maybe here now, EG cross Cn minus 0, quotiented by G, because the form eta was G equivariant. But the next step in what we want to do is to compute this the associated cocycle, and it's not easy because it depends on the base point, and you have to pass from one translate of a base point to another one. So there is a lot of data to keep track of. So the computation are quite hard to make, and to simplify this, to compute, one would like to move the base point to a preferred place, and one wants to move the base point t0 to the boundary at infinity in X. So if you think in the two-dimensional case, in other words, we want to replace integral on a geodesic triangle inside the hyperbolic plane to integral on, in fact, in the case n equal 2, I should say that what we will really do is to replace integral on geodesic segment by integral on geodesic lines from one boundary point to another, and so we end up by in considering a modular symbol. It's not a surprise that it's easier to compute, to have nice formula with this. Think of the computation of the area of a triangle, for example, or I mean that's that gives much simpler formula. But in general, to do that, we have to understand what first. What does it mean? What is the boundary at infinity? And here there are several choices in higher rank. So which compactification to choose? And another question is that, can we really extend the form up to the boundary? And so that's the two questions I want to address today. And
really nice question. So in this two-dimensional case, it's clear what a geodesic simplex means. It's basically that the edges are geodesics and the triangles are obviously the. So
in fact, in the n equal 2 situation, essentially we are considering geodesic lines, because we go up to degree n minus 1, which is 2 minus 1, 1. And in general, what you will do is you order the element, and you first take the geodesic segment from G minus 1 T0 onto G naught minus 1 T0, and then you make the geodesic cone here from the third point, and when you have a fourth point, you make the geodesic cone on the triangle, and so on. So it's not that's one more thing that show that it depends on a lot of choice. So if you want to make computation inside the symmetric space, things are hard to compute, and you won't get a nice formula doing that. You have the class, but it's hard to compute. And so I want to go to the boundary and have simpler way to have simple computation.
So, and the geodesic simplices always exist in a higher dimensional case as well.
I mean, geodesics. Geodesics. You can always take the geodesic cone. I mean, it's not. So it depends on an ordering of the element.
Thank you.
So let me now say a few words on two classical compactification. So there is a whole world of compactifications of symmetric space. I recommend if you are interested, there is a nice book by Borel and G on this subject, which contains a lot of material. So here I will mention only a very few things. And the first natural way to compactify the symmetric space, or rather the space S G mod K that we have considered yesterday. Remember that this space is a space of Hermitian, positive definite Hermitian forms. And so it's natural to embed it as an open cone in the space, let's denote it by Hn, of rank n, symmetric Hermitian matrices. And again, here we have a natural G action to be coherent with my lecture of yesterday and also Louis' lecture yesterday. Remember that the action was the following. And so now, if we mod out by the positive reals, then we end up with an embedding of the symmetric space inside the projective space associated to this rank n Hermitian matrices. And so this is now a compact space. And this embedding is G equivariant. And so in that situation, so if you want to consider some compactification, you can consider the closure. And I will put a S because it's Satake compactification, and to be more precise, it's the minimal Satake compactification. And I will describe a bit this compactification and be a bit sloppy about the topology on it, but just to give you a sense of it. So it's, of course, there is the space in it, and you can add to this boundary component that I will denote BW. So here W is non-zero proper subspace of Cn, and BW is the subset of the projective space on the Hermitian matrices that corresponds to matrices H, such that the kernel of H is precisely W. So X is made of the positive definite Hermitian matrices, and we consider only so it corresponds. So the kernel of these matrices is trivial, but here we authorize it can now degenerate. It will still be positive but not definite, and it can have a kernel, and the part that I did not BW are exactly the matrices that have a kernel this subspace W. And in particular, this the matrices here are positive definite on a subspace of dimension n minus the dimension of W. So this is isomorphic to the symmetric space associated to SL n minus the dimension of W. So it's in the notation x is equal to xm. Okay, and if we want to remember the G action, in fact, we can decompose this Satake compactification as a disjoint union of G orbit of G orbits. So there is the G orbit which is the space X itself, and then you have the G orbit of xn minus 1, where you embed xn minus 1 in the canonical way inside xn just by forgetting the last coordinate, let's say, and so on. You have a disjoint union up to x1. But that's not so much the way I want to look at it. Now I want to I will use a notation that if W is as above a proper subspace of Cn, which is a non-zero proper subspace, then I will let xw denote the Satake compactification of the boundary part of the boundary part associated to W. So it's a contractible. It's convex, so in particular it's contractible, and it consists of Hermitian form that are positive but not definite, and such that the kernel contains W. Now you have more than just Hermitian form that have kernel precisely W. You can degenerate, and in that way we have. So it's no more a disjoint union, but we have that the Satake compactification is equal to X union all the XL where L are lines. You can first you first degenerate to you have one line along which it can degenerate, and then it can degenerate more. But so I will okay. So here I have only described this as a set. For today, I will be a bit sloppy. You can imagine you can try to imagine topology, but now I want to go from that to another compactification, and to do that, I will look a little bit at what happened at the boundary in the Satake compactification, and at the boundary, so you have a cover. We just described the cover by XL, and how do these covers intersect? So if L1 up to, let's say, LK are lines, non-zero lines, then the intersection, so I'm looking at finite intersection of these covers of the boundary, and this intersection is non-empty if and only if the subspace spanned by generators of the lines is a proper subset. And then this is equal to precisely this span. So in the end, it turns out that this, so in particular, since all these are contractible subsets, then the cover by the XL, where the L are lines, form an acyclic cover of the Satake covering, maybe, of the Satake boundary. So we have this this cover of the Satake boundary, and I want now to define. Let me say it like that. Definition. This is not the standard definition. The first barycentric subdivision of the nerve of this covering is called the Tits building. Tits building of associated to JNC. So let me explain what it means here. So we have a cover of the boundary. So the nerve of this cover, you put a vertex in each of the cover. So these vertices are associated to lines. You put an edge when two XL intersect. So you have edges here, and you put a simplex when there is a triple intersection of the. So this is the nerve. This gives you a simplicial complex, and now what is the first barycentric subdivision of this?
Sorry, what does acyclic mean here then in this covering?
It means that the intersection are contractible. Each of the intersection and further intersection are always contractible because of the equivalence relation. I just put this.
I see. Thank you.
Okay, and now the first barycentric subdivision, you put vertex in the middle of each edge, so it will correspond to an intersection of 2XL. So here I see 3 vertices, and the triple intersection corresponds to another vertex. So in other words, in the end, what are the vertices of the Tits building? These are precisely the non-zero proper subspace. Of Cn. And what are the K simplices? The K simplices are the strict flags that consist of non-zero proper subspace. Of K, K plus 1, yeah. And so So we have seen the vertices on the picture that they are associated to. So the red vertices are associated to lines. Maybe I should write this one in black. The blue vertices are associated to spans, to subspace that are spanned by two lines, and the black vertex is associated to the span with three lines, at the condition that these three lines still span a proper subspace. Okay, so that's the more standard definition of the Tietz building. And now I can mention that there is another compactification that is called the Tietz compactification. Of the symmetric space, where now at the boundary you precisely see the Tietz building, and this compactification, it's not obvious, but it's more in some way you can visualize it more geometrically, because it corresponds to the so-called visual or geodesic compactification. So it tells you how what are the geodesics that stay at bounded distance for until the end of time. If you are staying at bounded distance until the end of time, then you define the same point at infinity. If not, you define a different point. And when you do that, what you see at infinity is precisely the Tietz building. So somehow it captures something very geometric on the symmetric space, at least from the point of view of geodesic. So in this way, you can think of a point in the of a points in the Tietz building as a direction, yeah, and so I will refer to I will be a bit sloppy and refer. I will to a subspace, a proper subspace, a non-zero proper subspace in Cn as a direction at infinity, except that I'm a bit sloppy here. I should really, since you see the whole Tietz building, I should, yeah, maybe I should not say that. It's a bit too sloppy. So I will refer to a K-simplex. So K-simplex is a flag in TNC as a direction at infinity, and along this direction, you can understand how the Hermitian forms that are remember that point in X are Hermitian forms, and how they degenerate, and along this direction, along which the Hermitian form, the main contribution is something like that. So I'm not saying that it goes exactly to this, but there is some terms, and in somehow it's the same. It's the main contribution term. You project using the orthogonal. Here, orthogonal refers to the fixed base point in the symmetric space, associated to our choice of maximal compact subgroup. You take the orthogonal to the biggest space of the flag, and the orthogonal projection squared give you a degenerate Hermitian form that will contribute until the end of time I mean, your form degenerate, but you still have this this contribution. And why am I insisting on that? Because remember that in the end we want to understand the behavior of our form that have a Gaussian behavior, and where the Gaussian is associated to the Hermitian form at the point on the symmetric space. And so I want to understand how the form evolve in the direction of some flag. And so from this, it's not hard to show the following fact, that in the direction so again, I put in the direction of this flag, the form eta restricted to x cross some kappa, where kappa is a compact subspace of Cn minus Wk. So when you have a point Z in kappa, it's a compact subset outside Wk, so it has a non-zero projection with the lower bound on the. I mean, it's the projection on the orthogonal to Wk is non-zero with a uniform lower bound, and so the form eta extends to a closed form on both, in fact, on both this, and it's also true, but I don't need to consider all flags, so I just put it in bracket. I will concentrate on the sorry, the bracket at the. I will concentrate on the Tits compactification. Just a few words on the Satake compactification, and so it can extend in such a way that it vanishes at infinity. So you understand, we are converging in a direction where at infinity there is still a contribution of in the Gaussian form of this degenerate Hermitian form, and since we are outside Wk, this contribution will give 0 when we go at infinity. And why 0? Because when we go at infinity, I said this is the main contribution, but also it gets multiplied by some. Remember that we are in a cone, and the boundary at infinity, we are multiplying by t that tends to infinity. So
just to understand the Tits building better, in the case of SL2C, where you have the hyperbolic 3 space, the visual boundary is the sphere at infinity.
Yeah, in that case exactly. The boundary here is just the sphere at infinity. Yeah.
Okay, and it is true that if you take two geodesics in the hyperbolic 3 space in the interior.
I didn't get the question, I guess.
Sorry, I was just trying to understand the Tits Tits boundary or the visual boundary in the hyperbolic 3 case in terms of the geodesics ending.
In the hyperbolic 3 space, this is just the sphere at infinity, except that in that's where you I mean, except that somehow the point I have been very sloppy on the topology, and since we put the discrete topology on GL2C, the point of the sphere are discrete. I mean, it's a discrete topology. It's a sphere with a discrete topology, so in some sense. But it tells you that if you go there is as much direction as there are points in the sphere at infinity. Okay, and when you point to a direction at infinity, it tells you what how are your Hermitian form degenerating. So maybe even before SL2C, just SL2R, when you are going from 0 to infinity, then the form that you see on this geodesic are of the form when you go to infinity, only one of them contribute, and I mean only I don't know, it's x squared that contributes if you go to infinity, and if you go to 0, it's y squared that you see at infinity. And so in the Gaussian, if you are, for example, if you are away from the plane x equals 0, then certainly, if you are in a compact subspace that avoid x equals 0, then the Hermitian form you see in the, I mean, when you see in when you see this in the Gaussian part of eta, so eta has something like that times other stuff, but which are at most polynomial. So if you are away from x equals 0, it means that x is non-zero. So when you go to this and let t tends to infinity, then this will decrease very fast and tends to 0. And so that's what happened in a more general situation. Okay.
Great, thank you.
And now I want to relate these boundary things to modular symbols. So this will be my second part. Modular symbols, and they will be associated to a k-tuple of, I mean, first I will consider a k+1, sorry, tuple of vectors in Cn minus 0, so non-zero vector. And from this, I will associate a map from the the standard K simplex, except that I will consider the barycentric subdivision of the standard K simplex to the Tits compactification. And I will distinguish two cases. The first case is if K is less than n-1, or if the span of the Qi is a proper subspace, then the image is completely contained in the boundary of the Tits building, and we associate the following simplices. So the vertices are the line spanned by these vectors, but also the planes spanned by two of these vectors, and so on. So as long as the space spanned by this K+1 vector is a proper subspace, all these subspaces are proper, and so you have a triangle in the, you have a simplex, a subdivided simplex in the boundary at infinity. So this is contained in that case in the boundary of the Tits compactification. And now what is really called a modular symbol is the case where K is equal to n-1 and the vector span from a basis of Cn. Then we define the map in barycentric coordinates as the combination of some rank 1 forms. So the MJ are, I can write what it is, but so I will explain what, so it's an Hermitian form of rank 1 such that the kernel of MJ is precisely the subspace by all the Qi except Qj. And in fact, to have a formula, it's not, let me just say that I define the Qi star as inverse transpose of the matrices with column the Qi. But the important thing is this, is that it is a rank 1 Hermitian form with kernel this. So the boundary of this triangle is really at infinity. Okay, it has. I mean, the vertices you see at the boundary are all the subspace spanned by vectors that belongs to the Qj, all the proper subspace spanned by vectors that belong to the Qj, and then you have something that goes in the interior of the symmetric space. So it's in the case n equal 2, it's really a geodesic. You have at infinity, you have a rank 1 form, and you are considering all the Hermitian forms that are a linear combination of this convex combination of these two rank 1 forms. And it's so the whole interior of the simplex is contained inside the symmetric space. And these are the H-Rudolph modular symbols that were considered, that were mentioned in the talks by Paul Gunners. And once you have that, now the question is, what is the value of our form? Can we integrate our form on these modular symbols? And what is the value of this form on the modular symbol? And that's the beauty of the Matta equivalent form, is that it's very easy to compute. So that's the next thing. It's evaluation of eta along modular symbols. And first, note that the fact implies that if you consider the form that I will denote eta of q, which is the pullback by the map we just defined, the map delta q, times the identity on the fiber Cn, and you pull back our form eta. So this is a form of degree 2n minus 1 on the subdivided simplex delta k prime times Cn, Cn, and I will erase all the hyperplanes that corresponds to the direction where you want to go with the modular symbol. So what are these hyperplanes? It's all the, I will say WQJ, where WQJ is precisely the hyperplane, I mean, it's spanned by, yeah, I should have said that Q is Q0 up to Qn minus 1, and I forgot Qj. And it's a basis Okay, so I'm really considering now the case of modular symbols. In fact, yeah, I could do the same. Yeah, no, it's stupid. Sorry. At that point, so it's not hyperplanes; it's a subspace. Anyway, okay, so I erase these subspaces because away from this, the form decreases very fast in the direction of these of all the points you see at infinity, and so you can integrate the form, and it gives a closed form. And the proposition is that one, if the subspace spanned by the QK is a proper subspace of Cn, then because we have precisely erased all this direction, then and we are integrating on something that sits only at infinity, then the integral is just 0. Is 0, and I want to write it like that because remember that it's a partial integral. So the form here is a form that is on delta k prime times something in Cn. So you integrate only on delta k prime. So this, of course, is 0, but it's 0 as a form of degree 2n minus 1 minus k. So it's minus k plus 1 over, and it's defined now on Cn minus this subspace. Okay, so I'm here. I'm in the case where we are completely at infinity, and now, of course, the interesting case is what happens if k is equal to n minus 1, and the span is c to the n. Then the integral of dk prime, so it's n minus 1 of q, is of eta of q, sorry, eta of q is 1 over 4i pi to the n dl naught over l naught minus dl naught bar over l naught bar wedge up to dl n minus 1 over ln minus 1 minus and this again is a form of degree n now on Cn minus all the hyperplanes. And now these are really hyperplanes. And what is Lj? Lj of Z is Qj star of Z, which is the linear form of kernel, the hyperplane WQ of J. So the one generated by all the Q minus J. And so that's a bit of a long statement, sorry. But what I want you to remember is that if the partial integration on these simplices, if the simplices are at infinity, then it's a 0 form, at least away from some subspace. And if if you are working with the modular symbol that go inside the symmetric space, then you erase all the hyperplane you see at the boundary, and on this is it's a very simple differential form. That is and that I have just written, and the proof is quite elementary. So the first part is just that because eta vanishes at infinity in this direction, because we erased the relevant hyperplanes. And in the second part, we can reduce by using the G invariance. We reduce to the case where Q0 Qn minus 1 is just the standard basis, E1, En. And so in the SL2 case, we are really integrating on the geodesic that go from 0 to infinity. And here we are integrating eta on the orbit under the diagonal matrices A, K, and remember, we are at the quotient by the positive reals here. So where A are the diagonal matrices Tn, where Tj are the Tj are positive, and the product is 1. But now, I don't know if you remember, but the form eta was obtained as a kind of Mellin transform of psi. And I insisted to say that, in fact, this Mellin transform of psi can be seen as a period of phi, because phi was decomposed as some form, remember, alpha wedge plus psi wedge d s over s. So in fact, integrating on the one more variable, which is the R positive real here, it's the same as taking the period of phi. So in fact, this is the same as the phi here. And here you integrate over n variables, n positive variables, as always the compact space K. And because of the functoriality of the math-equivalent formalism over this R positive to the n, the bundle is decomposed. The bundle is decomposed metrically as a direct sum of bundle of rank 1. So in fact, we are reduced to the rank 1 situation, and so it's just the wedge product from 1 to n of the integral of the phi j. And so this is the rank 1 situation. And we have computed eta in that case. In that case, eta is precisely 1 over 4 pi I d zj over zj minus d zj bar over zj bar. And that's exactly what we wanted to prove in that case. So you see, the point is that using this math-equivalent formalism, we completely avoid any technical computation. We are just reduced to the rank 1 situation, because along the geodesic, the bundle, think of the n equal 2 situation, the rank 2 bundle splits as a direct sum, metrically, as a direct sum of 2 line bundles. And that's all. And now, what is the benefit of all this? Is that now we can compute easily the cocycle, the GLNC cocycle. So let me conclude with this. At the beginning today, I started with a map that goes from the simplicial set to the symmetric space after the choice of a base point. But now, what I'm saying is that if we are away from of some hyperplanes, and precisely what I will do is restrict to U prime. Remember the notation. U prime is associated to the tuple of element in G and one vector in Z, such that you ask that if J is bigger than N, is smaller than N, then Z does not belong to the span of the what I have denoted Qj, where I remember Qj was Gj minus 1 E1. So if you want, what we have done here is we have taken one of the deepest points in the boundary at infinity, the one that corresponds to the line spanned by E1. And so we have moved the base point to this line. And we do exactly the same business as earlier. We will have a simplicial map from EG cross Cn minus 0 to not only x, but the Tits compactification of x. And what we do is that we to a bunch of elements G0 up to Gk and to an element Z, we associate. So when I take the geometric realization and we associate a point and the vector Z, where this point belongs to delta of Q using the barycentric coordinates. And delta of Q, where Q is G naught minus 1 E1, etc. G K minus 1 E1. So we in more geometric terms, we consider at infinity G0 minus 1 E1, G1 minus 1 E1, and we draw the simplex or modular symbol that are associated to this. So if k is less than n minus 1, all the simplex sits at the boundary at infinity. But as soon as k is equal to n minus 1, we are inside the symmetric space. And so when we do that, in fact, what we are doing is that we are making explicit the computation in the spectral sequence, because as long as we have in degree k less than n minus 1, we are at infinity, and we will find 0. We will find 0 if we restrict to not to Cn minus 0, but to Cn minus the relevant hyperplanes. So in the end, we have to erase all the hyperplanes, so we have to restrict to U prime. So we replace this by, we replace this by U prime. And here we replace by erasing hyperplanes here. And so that's how we define the form. So I should say that, yeah, we have this new row. Let me rho bar or rho infinity. And what we have done is taking the pullback of eta by rho bar and restrict it. I should say it's here really that we restrict it to prime, and we get a new we get a well-defined form that represents the same cohomology class, because in restriction to U prime, we have the right to go to infinity. And so in the end, corollary, or this defines the cocycle. And that I will denote, yeah, I don't know why I put it corollary. Define the cocycle that I will denote S affine. And the corollary of the previous computation, S affine of G0 up to Gn minus 1 is precisely equal to 1 over 4 pi I n dl1 over L1 minus dl0, sorry, over L0, dL0 bar over L0 bar, wedge dLn minus 1 over Ln minus 1 minus d. And now Lj, again, Lj is a linear form of kernel G not E1. We forget about Gj minus 1 E1 and Gn minus 1 E1. And so, and there is no term before, because when you take less than n minus 1 n element, the form vanishes at infinity. So there is no term. So we have computed like in the spectral sequence by erasing the hyperplane, and we have made all this concrete. And now to conclude my talk, again with a few minutes late, sorry, is that now we can use Briscoe theorem that I recall. That the map from I denoted affine here, I think, from the cohomology of Cn minus hyperplane, which is really a limit, and that sends dl over L to the class, to the cohomology class it defines, which is the same as dl bar as a real part of it, is an isomorphism. So the fact that this map S affine defines a cocycle implies that in fact it defines a cocycle already at the level of meromorphic form. So S affine lifts to a cocycle in which is given by the formula 1 over 2i pi n d L naught over L naught, wedge d L n minus 1 over L n minus 1. And that was the cocycle I mentioned in the first lecture. That's so I mainly work today with the Tits compactification because it's a richer one that gives you the cocycle that is not so obvious. It is indeed a cocycle. If you do the same with the Satake compactification, so you can still go to the rank 1 form at the boundaries that are given by translating by taking, instead of taking the sorry. You work dually in the at the boundary, and then you will get the other cocycle I mentioned in my first lecture, and that's also why there are cohomologous. Is that because they all come from the same class at the origin. Okay. So I will stop here today. Just let me say that in the last lecture, I will do exactly the same, but after replacing eta by a Eisenstein series. So after averaging by a lattice, and then we will end up with with arithmetic cocycle, whereas this one, of course, has no arithmetic in it. Okay, yeah, I stop here.
Okay, let's thank Nicolas. Are there any questions?
Just a small comment. I think you mentioned it right at the end, but I just want to clarify. If we go, so at some point you mentioned that one can integrate eta over the modular symbol running from 0 to I infinity.
Yeah.
In the rank. And so is eta over here a modular? I mean, is it a modular form of weight too, by any chance?
I mean, no, at this point, no, but because it's there is no arithmetic, but when I will form an Eisenstein series by somehow average eta, but in a regularized way, then I will get an Eisenstein series, but that still depends also on the fiber. But if you pull back by a torsion section, it wants to be a weight 2 modular form. Yes.
I see. Okay.
In the n equal 2 case.
Yeah. Thank you.
So I have a small question. This is probably anticipating on your lecture tomorrow as well. So when you have a normal Eisenstein series on GL2, then we can't really associate to it a modular symbol, right? So one can't integrate Eisenstein series. But your approach gives us a way of making sense of that somehow.
No, I mean, for the moment, that will be all the point tomorrow. I mean, but I can a little bit explain what here before averaging the form. If you want to integrate to go to infinity, it's not that hard. You just have to stay away from some hyperplanes on the fibers. But now, when you will average the form, then you will have to stay away from some hyperplanes, but still be in the averaging, in the regularizing procedure to build the Eisenstein series. It will not be enough. It's a bit like the standard thing that when you look at an Eisenstein series, the poles that can come from both phi at 0 and the Fourier transform of phi at 0. So you have to be careful of both things. So there will be a further condition on the test function at finite places you want to make, or another way on the lattice with respect to which you average, and on the finite linear combination of lattice you consider. And so this condition is precisely what Louis were referring to yesterday as a smoothing. It means that you can smooth, you can choose in the right way the finite test function, so that after this choice, which amounts to a smoothing, you can integrate on partial modular symbols. Of course, Eisenstein series should not be cuspidal, so you cannot hope to be able to integrate on all modular symbol, but if partial modular symbol is okay after some smoothing.
Are there any other questions?
Hi, quick question. So this averaging of eta, is that the same technique that was used by Bismuth and Giger?
Yeah, I mean, essentially, I mean, it's the usual Eisenstein series regularization. So yes, that's I mean, we are not so in some ways, Bismuth and Giger are more general, meaning that they consider they are not limited to symmetric space and so on, but there is no group structure on it, and they don't work on the they work on the base, because what they are really interested in is transgressing the Euler class on the base manifold. And what we are doing here is working on the bundle, and so you have to follow what happens with the variable in the fiber, and all these hyperplanes complements you have to consider, and so on. But the regularization procedure, yeah, it's the same. I mean, we should call it, I guess, Kronecker regularization. That's doing Eisenstein series. Consider the Poisson summation formula to yeah, that's the old one that you all know in arithmetic. Yeah.
Are there any other questions? I actually had one question about the chronology of the project you've been explaining to us. So, I mean, at which point did you guys have the insight that you would want to erase hyperplanes? Was it that you sort of started with this differential form and realized you would want to push the base point to infinity, and you sort of noticed this convergence issue, or?
I remember vividly the precise we were discussing. I was complaining that okay, we can make all computation. The only problem is that when we reach these hyperplanes, and then Akshay told me, but okay, just erase hyperplanes, and my problem was that, yeah, but there are if you erase all the hyperplanes, then there is nothing left, and then we started to, and he said, okay, well, let's do it equivalently. Let's try to erase, and that was the start. So yeah, it's really the issue was really from what I told you today. I mean, it's hard. It's easy to compute this integral using the matter-equivalent formalism, but you have a problem when you sit on the hyperplanes, and sometimes the simplest answer is just the right one. Just erase the hyperplanes.
Yeah, because it seemed from the I think from one of your first lectures, like the way you described the erasing of hyperplanes, I wasn't sure whether that was just sort of like a very useful device for being able to actually compute something, or whether it was sort of whether it was fundamental to the whole.
No, in the end, it turns out to be fundamental, but at the beginning, it was a useful device. I mean, one very so matter-equivalent construction is very nice because it produces formula, but one problem is that it produces real differential forms, and what I like in this general theory, which I don't know if it's very important or not, but it's just something that motivates me to do this, is that it makes links between topological things, the topology of real manifold, like quotient of the symmetric space of SLN R, and some algebraic object like meromorphic form. And this, there is a you don't see it in the matter-equivalent construction because it's real forms. So you have this cocycle between cohomology class, but why would it live to meromorphic form? And so we were trying. So the first attempt is to try to cut the matter-equivalent form and to keep only the part that wants to be holomorphic. So the N0 part, if you want, of the form, and ask, is the global form you get closed and still define a cocycle? And we were struggling with that, and it was not clear at all. But once you erase hyperplanes, on the purely topological side, you see that you killed all the cohomology in the fiber because it becomes affine up to a sufficiently big degree. And then in the affine case, there is the Briscoe theorem that tells you that all the cohomology is in fact given by meromorphic form. So it was a kind of a gift, a bonus from the fact to erase hyperplane. So it was an indication that we should erase hyperplane then. And then we wondered, in the case of hyperplane complement in elliptic curve, in product of elliptic curve, or hyperplane complement in a product of GM, is there still a Briscoe theorem? We first try to look in the literature, and in fact, no. there is only such a theorem if you decorate by some local systems. And that's not so surprising because it's related to what Johannes discussed. If you decorate by some local system, you kill a lot of cohomology. And so you may hope that everything is described by some simpler complex. But if you take the trivial local system, it's not clear. And so the other thing to do, which is completely parallel to the taking the polylog local system, is to keep the trivial local system, but to stick to the part that is stabilized by the push forward, by the multiplication by S push. So then you look only at this part of the cohomology. And now question, maybe this part can be represented only by meromorphic forms. And that's true. So that's what we prove. So that's yeah. Maybe it was a bit long.
No, that was a great answer to my question. Thank you. So if are there any last questions?
Just a small comment. It's so still, I mean, there's no arithmetic meaning to this integral of eta over these modular symbols, but it's nonetheless a period in the sense of Conservation-Zagier. There's one form that you're integrating over a cycle, and it's nonetheless an interesting number.
I mean, be careful. It's only a partial integration. I mean, I don't know exactly what. I mean, what I have described today, it's only a partial integration. So what you get is a form. So I'm not sure it qualifies as a period in the sense of Conservation-Zagier.
Thank you. I'll see you.
I have a quick question about what you were just talking about.
Sorry,
Peter, we lost you.
Yeah, someone muted me, which was.
Yeah, no, I did it by accident. I wanted to. Okay, fine.
Oh.
There, sorry.
Sorry, I don't think I'm in a fit state to start my video right now.
Okay, fair enough. Okay, no problem.
But okay. Anyway, my question is: what you just said that like the isogeny fixed part of that cohomology being represented by meromorphic forms. I just want to try to understand what you're referring to from that. Was that from the Takagi notes? Like, are you referring to them?
No. It's I mentioned it, but very quickly at the end of the second lecture because I was running out of time, and I'm a bit cheating because it's an important part, but that I have skipped. Is that once you have a cocycle with values in the cohomology, then to get meromorphic form, you have to say something, and so you have to say that it can be. That the cohomology can be represented by meromorphic forms, maybe with singularities along these hyperplanes. That's exactly what does Briscoe theorem for you in the affine case. And the question is that is it still true in the if you replace Cn by let's say C star to the n minus hyperplanes.
Okay.
And the answer, I don't know. I don't think it's true. But if you stick to the part that is fixed by 1, then now it's true that everything can be represented by meromorphic forms.
So there's some kind of formality theorem on that part of the cohomology. Is that what you're saying?
That's not the way I see it. So I wouldn't say it exactly like that, but that's really the way I see it. It's really a Briscoe theorem that, and in fact we used to do that. The thesis of Clément Dupont that proved that we proved tell more about the Briscoe theorem. So he considers natural meromorphic forms associated to an hyperplane arrangement in a general very general setting. You take some complex manifold. You take the product n times. You consider hyperplanes arrangement in this, and you consider the meromorphic form that are very special. I mean, that are a product of holomorphic form with df over f, where the f are the coordinates that define the hyperplanes in your and the natural question is that how much of the cohomology you capture using this
I see.
and
this applies equally to the trigonometric and the elliptic cases?
Exactly, it applies equally to the both cases. Yeah.
Cool. Are you going to talk about this tomorrow, or?
I know. I mean, yeah, that's something I have put under the carpet, but
Okay.
But yeah, if you are interested, I can share some. I can
Yeah, that'd be. I'll email you. That sounds really good. You said also there was the thesis of Clément Dupont that has.
Well, the thesis of Clément Dupont is now published in Annales de l'Institut Fourier. So this the statement we need is not in the thesis, but there are a lot of important tools that are in the thesis. So
Okay, I'll take a look and I'll email you later. Thanks.
Are there any other questions? All right, well, if not, let's thank Nicolas for another very nice lecture.